Second one's telling us that angle 1 and angle 2 are vertical angles, and that's what vertical angles are. We've seen this picture before. And we know about the vertical angles.
Please, we do have one bus still on the route, so students will be coming in tardy. Please do not count them tardy when they arrive if they were on that bus.
That wasn't any of you, was it? Good. All right. So continue on. So angle 1 and 2 are vertical angles, and we know that angle 1 and angle 2 are supposed to have the same measure. All right, this is one of those things we've learned already, but we want to prove it. All right, this is the vertical angle theorem. Okay, a theorem is like a postulate, except it's not as set in stone true. It's not as believable. All right. So postulates are very believable. Nobody has to doubt it. It's like, obviously, yes, that's true. A theorem is more like, it seems like it's true, but you got to prove. You got to convince me. All right. So that's what a proof is. And just to give an extra name here, I'm going to call this angle 3 right here. If I'm using numbers, letters to represent angle measures like that, angle 1, angle 2, angle 3, then I don't have to write angle ABC or whatever. I can introduce some variables, like I put this as point A, this is point B, and this is point C, for example. Now it's angle ABC, but angle 1 is a lot easier to write. Right? So if you ever have a picture with your proof, however you label your picture, you have the capacity to use those labels in your proof, and it limits the amount of stuff you have to write, because you've got to write a lot of stuff in proofs. So the first step of any good proof is to restate your given information. Okay? So step 1, I'm going to write angle 1 and angle 2 are vertical angles. Because it's given. When it comes time to do a test or a quiz on this, and a proof is on a test or quiz, that's free points right there, because I say free, not three, free points. Because I give partial credit on proofs. If you get part of it right, you're right that much, and that's the right step. Okay, every single time. Write down what's given, and say given, and you've gotten some points right away. The rest of this stuff doesn't make any sense whatsoever for the number of proofs we're going to have in this class. At least getting those few points might bump your grade up enough to the point where you're more comfortable. So I don't want you to be freaked out by these things, but again, they're a little bit lengthy for most people. So this one's not so bad. Now the next thing, you can say I've introduced angle 3 up there. Here's my thought, and before I start actually writing the whole proof out, I kind of want to have an idea of where I want to go with this. All right, so here's where I'm going with this. Would everybody agree, disagree if you wish, but this right here, let me use a different color. That's a straight line. Supposed to be right on top, give it a straight line. Straight line, right? Mm-hmm. What can we say about angles 1 and 3?
In all?
Yeah, what's true about angles 1 and 3? If the blue line's a straight line, what's true of those two angles?
They're adjacent.
They are adjacent. What else is true about them? Again, the straight line matters.
Together, they're 180.
Together, they're 180 degrees. Can we all agree with that statement? Okay. That blue line is obviously a straight line. Straight lines we can see with our eyes. They don't bend, they're straight, right? That doesn't bend at all, it's a straight line. So 1 and 3 make a straight line, so 1 and 3 have to add up 180. So my next statement, okay, now listen to this statement I'm about to say. If two adjacent angles form a straight line, then they add up to 180. That's the if-then statement. If, all right, two adjacent angles, and Blaine already said they're adjacent, right? Adjacents share a side. If two adjacent angles form a straight line, see how the if part's been satisfied, right? We've been doing all this if-then stuff recently. The hypothesis has been satisfied, so by the law of detachment we can say that angle 1, measure of angle 1, plus the measure of angle 3 equals 180 degrees. And again, the if-then statement says if two adjacent angles form a straight line, then they add up to 180. I'm going to say 180 degrees in a straight line. You want to write the whole if-then statement, you sure can. Now notice I didn't write down that angle 1 and 2 are adjacent, they form a straight line. Again, I can see that with my eyes. The picture gave me that information. So sometimes the picture is going to give you information. Again, if the hypothesis of an if-then statement is satisfied, the conclusion can be drawn. This is the conclusion, right? They add up to 180. So, would everybody agree that this is a straight line? Red line is a straight line also, right? So what can be said about angles based on that red straight line?
Angles 3 and 2 add up to 180.
Couldn't we say the same thing? So 2 and 3, straight lines, so they're adjacent angles that form a straight line. So it's the exact same reason for the statement, so I can put that on the second row too. So I'm going to say the measure of angle 2 plus the measure of angle 3 is equal to 180 degrees. If you put it on the, like next to it, put like a semicolon to continue it on, but if it's like next line down, you can do it like that, either way. Okay. Both of these have the exact same reason, so I can write them both as in the same place, right? If you want to write 3 and 380 degrees in a straight line again, you sure can. If I have multiple things with the same reason, I just write them all down, and then I put the reason. Everybody's comfortable with what's gone on so far? So now, up till now, all we have is these vertical angles. We can see the adjacent angles forming straight lines, so we were able to conclude this. Now we know this, that 1 and 3 add up to 180, and 2 and 3 add up to 180. So can we all see? This is used quite often when we're trying to prove an equation or something equal. When you're trying to prove a congruence or equality, and that should say angle 2, not square root. Does yours say square root of 2?
No, mine's the same.
It should say angle 2. I don't know. My math editing software must have been going haywire the day I made this up. Anyway, angle 1. Whenever we're trying to prove an equality or congruence, the substitution rule is going to be used quite often. All right, the substitution is based on this. If you have some expression equal to something, so angle 1 and angle 2 add up to 180, and then you have a second expression adds up to the same thing. Okay. That's what substitution requires. If two things equal the same thing, do two things equal the same thing? Two things equal the same thing.
Yeah.
Then
Substitute.
the two things equal each other. That's the substitution law. Substitution property of equality. It says if two things equal the same thing, then those two things equal each other. So I know that measure of angle 1 plus measure of angle 2 equals measure of angle 2 plus measure of angle 3 by substitution. I've been doing proofs for a long time, so I can kind of see how this is building up already before I even started. All right, you guys, this is the first proof you've ever seen in your entire life, so obviously you don't have the same vision I do on this. But anytime you're trying to prove something equals or something is congruent, first get the things involved in that statement, 1 and 2, into an equal statement. So 1 and 3, angle 3 is nothing about angle 3 up here, right? But 1 and 3 out of 180, I know that for a fact. You get angle 1 into an equation, angle 2 and 3 out of 180, get angle 2 into an equation, and then hopefully they have some relationship that gets them into the same equation. So now angle 2 and angle 3, or so angle 1 and angle 2 are in the same equation. And this, you see, you guys correct me when I mess up. I got to take this exact idea, right? This says 1 and 3, there's 1 and 3. This says 2 and 3, that's 2 and 3. Been counting the numbers all my life, 1, 2, 3, 1, 2 always follows 1, so sometimes my brain just wants to throw in the wrong number. So 1 and 3 out of 180, 2 and 3 out of 180. So 1 and 3 and 2 and 3 equal each other. Now, at this point, this is what I want. Angle 1 equals angle 2. I actually want their congruent, right? But that's later, right? We gotta be equal first. Yes, Esteban?
Then you do like, how would you divide by n angle 3?
You're in the right ballpark, but do not divide. Something else. Right now we're adding angle 3, right? So we're going to undo addition with subtraction. We're going to subtract. So what Esteban's noticed here is we have exactly what we want. This angle 3 is in the way, right? So we want it to go away. And he remembers from algebra that you're allowed to subtract the same amount from both sides of an equation if you wish. So I don't know what angle 3 equals, but I know this and this are the same amount, right? So whatever it is, angle 3 is 72 degrees and then 72 degrees. They're the same number. So what I'm going to do is I'm going to subtract the measure of angle 3 from both sides. So if I do that, if I subtract those measures of angle 3, like so, to write down then what is left will be measure of angle 1 equals the measure of angle 2. Not what we want to say. We want to say angle 1 is congruent to angle 2. We'll worry about that in a second. But can everybody see that subtracting angle 3 from both sides makes it go away on this side, makes it go away on this side, leaving us with exactly angles 1 and 2 in the same equation? And the rule for that is the subtraction property of equality. Again, the subtraction property of equality says if two things equal each other, then you can subtract the same amount from both sides. Two things equal each other, I subtracted the same amount from both sides. Again, I'm using law of detachment every single time on these problems. Each time I use law of detachment, and if part's been satisfied by what I have in my picture, I conclude with what I'm allowed to do. So if two things equal each other, then we can subtract the same amount from both sides. I did it. That's what allowed me to do it. Finally, if you want to prove congruence, first prove equality. Here's what the definition of congruence says. If, pick your geometric shape. It's definition of congruence of angles, definition of congruence of segments, whatever. If two angles have the same measure, then they are congruent. If two segments have the same measure, then they are congruent. It's just, that's how it goes. So, I'm simply going to state now, my final statement is going to be angle 1 is congruent to angle 2 by the definition of congruent angles. Notice the little m in front, measure of angle 1 changes to angle 1. When it says m angle 1, it's talking about the angles measured as a number. When it says angle 1 with no m, it's talking about the picture itself. And this proof proves that vertical angles are equal. So anytime we see that picture, we can know for a fact that angle 1 and angle 2 have the same measure.
Is it called definition of what?
Congruent angles. I apologize for my poor handwriting, but I can't put my hand against the board. I'll try and. When I face the board directly, it's easier. Is that better? So, and that's the general proof there. That's, as far as proofs are concerned, that's not a very hard one, but for the very first one you've ever seen, it probably seems kind of hard, okay? If you look back on this after we've done proofs for a couple months, you're going to say, well, that's a pretty easy one, all right? Right now you're like, I'm not sure I want to do this anymore, but you're stuck because you can't change your schedule, so you'll be fine. You'll manage. But again, state the given information. So this happened, right? And through a bunch of logic, this happened. So if this happens, then that happens. And it's just a bunch of law syllogism at that point, right? If this, then this, then this, then this, then this, and so on. So that leads to that, as we can see.